Download this code and get free GPT-4o from codegive.com, link in the description below. Certainly. In this tutorial, we will learn how to read a PWM, pulse width modulation, input signal using an stm32 microcontroller. This is commonly used to interface with radio control systems, such as remote control airplanes, drones, or cars. ### prerequisites. 1 stm32 development board. You should have an stm32 microcontroller, example stm32F103C8, stm32F4 series, etc. 2 stm32 Cube IDE. Install stm32 Cube IDE for development and programming. 3 Basic knowledge of C programming and familiarity with embedded systems. ###Understanding PWM. PWM signals are typically used to control the speed of motors or servos. The signal consists of a square wave where the width of the pulse, duty cycle, determines the position or speed. For example, in RC applications, a PWM signal can range from 1 millisecond to 2 milliseconds pulse width, corresponding to 0% to 100% duty cycle. ### Hardware setup. 1. Connect the PWM signal. Connect the PWM output from the RC receiver to an input pin of the stm32. For example, you might use pin PA0, PO pin 0. 2. Power supply. Ensure your stm32 board is powered, typically through USB or an external power supply. ### Software setup using stm32 Cube IDE. 1. Create a new stm32 project. Open stm32 Cube IDE. Create a new stm32 project and select your specific stm32 board. 2. Configure GPIO. In the Pinout End Configuration tab, configure the pin where the PWM signal is connected as a TIM input capture. For example, set pin PA0 to TIM2_CH1. 3. Configure timer. In the Configuration tab, select TIM2. Set the prescaler and counter mode according to your clock configuration. Example, if your system clock is 72 MHz, set prescaler to 72 to 1 to have a 1 MHz timer. Enable input capture on the selected channel. 4. Generate code. Click on the project menu and select Generate code. ### Coding the application. Open the generated project and go to main.c. Below is a sample code snippet to read the PWM signal using input capture. C. #include main.h. tim_handletype def_tim2. Volatile uint32_t pulse width equals 0. Void hal_tim_ic_capture callback, tim_handletype def**tim. If tim-instance equals tim2 / capture the pulse width. Pulse width equals hal_tim_read captured value, tim_channel_1. Void system_clock_config, void. Static void mx_gpio_init, void. Static void mx_tim2_init, void. Int main, void. hal_init. System_clock_config. mx_gpio_init. mx_tim2_init. / start input capture. hal_tim_ic_start_it, and tim2, tim_channel_1. While, 1. / convert pulse width to milliseconds. / assuming timer clock is 1 MHz, thus 1 tick equals 1 us. float pulse_time _ms equals pulse width /1000.0 / convert to ms / process the pulse_time _ms as needed. Static void mx_tim2 init, void tim_ic init type def sconfig ic equals 0. tim2.instance equals tim2. tim2.init.prescaler equals 72 to 1, / adjust for your clock. tim2.init.counter mode equals tim_counter mod_up. tim2.init.period equals 0xFFFF / max value. tim2.init.clock division equals tim_clock division _div1. hal_tim_ic_init, and tim2. sconfig ic.ic polarity equals tim_ic polarity _rising. sconfig ic.ic selection equals tim_ic selection _directy. sconfig ic.ic prescaler equals tim_ixc_div1. sconfig ic.ic filter equals 0. hal_tim_ic_config channel, and tim2, and sconfig ic, tim_channel _1. void systemclock_config, void / configure the system clock here, auto-generated. Static void mx_gpio_init, void / initialize gpio here, auto-generated. / add error handler, void error_handler, void while 1. ## explanation of the code. 1 hal_tim_ic_capture callback. This callback function is called whenever a pulse edge is detected. It reads the captured value from the timer. 2 pulse width. This variable stores the width of the last captured pulse. 3 main loop. In the loop, the pulse width is converted to milliseconds. You can use this value to control your motors or servos. 4 timer configuration. The timer is configured to count in microseconds, which helps in accurately measuring the pulse width. ### tips for debugging. Use a logic analyzer or oscilloscope to visualize the PWM signal and ensure it is being captured correctly. Check the timer's prescaler and clock settings to ensure the timing calculations are accurate. If you are not receiving expected values, verify the signal integrity and connections. ### conclusion. You have successfully set up an stm32 microcontroller to read PWM signals from a radio controller using input capture on a timer. This can be further expanded to control servos or motors based on the received PWM signals. Happy coding! Sure. Reading a PWM, pulse width modulation, signal from a radio controller using an stm32 microcontroller can be achieved using the input capture feature of the timer peripherals. Below, I'll provide you with a step-by-step tutorial on how to implement this, along with a code example. ### overview. 1. Understand PWM signal. PWM signals consist of a series of pulses that vary in width. The width of the pulse represents a value, which in the case of a radio controller, usually represents the position of a joystick or switch. 2. STM32 timer configuration. You will configure a timer in input capture mode to read the PWM signal. 3. Code example. I'll provide code using STM32 HAL, hardware abstraction layer, for simplicity. ### required tools. STM32Cube IDE or STM32Cube MX for configuration. STM32 HAL library. ### Step 1. Configure the STM32 environment. 1. Create a new project in stm32cube IDE or stm32cube MX. 2. Select your stm32 microcontroller. 3. Configure the clock, ensure the system clock is set properly. 4. Enable timer. Go to the timers section. Enable a timer, example TIM2. Set the timer mode to input capture and select the appropriate input channel, example channel 1. Configure the timer's prescaler and auto-reload register, ARR, according to your PWM frequency, example 50 Hz for RC signals. 5. Configure GPIO. Set the corresponding GPIO pin, example PA0, as alternate function mode for the timer input. 6. Generate the code. Click on project-generate code. Step 2, write code to read PWM signal. Example code. Here's a sample code for reading the PWM signal using stm32 HAL. C. Include main.h. / global variables. tim_handle def tim2. Volatile uint32 t pulse width equals 0, / pulse width in timer ticks. Void hal tim ic capture callback, tim_handle def * tim. If tim-instance equals tim2 / capture the pulse width. Pulse _width equals hal tim read captured value, tim _channel _1. Void system clock config, void. Static void mx GPIO init, void. Static void mx tim2 init, void. Int main, void. Hal init. System clock config. mx GPIO init. mx tim2 init. / start the timer in input capture mode. Hal tim ic start it, and tim2, channel 1. While, 1. / main loop. / you can process the pulse width value here. Hal delay, 100, / just for demonstration. Void mx tim2 init, void. Tim ic init type def sconfig ic equals 0. tim2.instance equals tim2. tim2.init.prescaler equals 0, / adjust prescaler for your timer clock. tim2.init.counter mode equals tim_counter mod _up. tim2.init.period equals 65,535, / max value for 16-bit timer. tim2.init.clock division equals tim_clock division _div1. Hal tim ic init, and tim2. sconfig ic polarity equals tim_ic polarity _rising. sconfig ic selection equals tim_ic selection _directy. sconfig ic prescaler equals tim_ixc div1. sconfig ic filter equals 0. Hal tim ic config channel, and tim2, and sconfig ic, tim_channel _1. Void system clock config, void. / system clock configuration code, generated by stm32cube mx. Static void mx GPIO init, void. / GPIO initialization code, generated by stm32cube mx. Explanation of the code. One global variable, pulse _width is used to store the captured pulse width. 2 hal underscore tim underscore ic underscore capture callback. This function is called when a capture event occurs. It reads the captured value and stores it in pulse underscore width. 3 mx underscore tim2 underscore init. This function initializes tim2 in input capture mode. Adjust the prescaler based on your timer clock and desired resolution. 4 main loop. In the main loop, you can process the pulse underscore width variable to determine the position of the input signal. ##### step 3, compile and upload. 1. Compile the code, build your project in stm32 IDE. 2. Upload to stm32, use a debugger or ST-Link to upload the firmware to your stm32 microcontroller. #### step 4, testing. Connect the PWM output from your radio controller to the configured GPIO pin, example PA0. Monitor the value of pulse underscore width in your code to see the changes as you adjust the radio controller. #### conclusion. This tutorial provides a basic framework for reading PWM signals from a radio controller using an STM32 microcontroller. You can further expand this example to handle multiple PWM signals or integrate it with other components in your project. Be sure to consult the STM32 reference manual for more details on timers and input capture functionality.